This is the 15th video in our series on Lie algebras, and today is the first step towards us proving a really important result, and that's a classification result for all semi-simple Lie algebras over the complex numbers. And now, throughout this video, we're going to take L to be a finite dimensional semi-simple Lie algebra over C. We're just going to set that at this moment so that we don't have to rewrite it many times. And then let's also recall the theorem that we had in the last video, and that says that L is semi-simple if and only if the killing form kappa, which is defined by kappa of xy equals the trace of add x add y, is non-degenerate. Okay. So let's maybe start with an example, and this example will show that SLNC is semi-simple. In fact, it's simple, but we're going to show that it's semi-simple. Recall that SLNC is the Lie algebra of all n by n matrices with trace 0. And I'd like to start maybe with the following observation, and this comes from a homework exercise from the previous video. And that is, if we take x and y in SLNC, then that means this killing form of xy is actually simply 2 times n times the trace of xy, the product of the two matrices x and y. And what's nice about this is that we don't have to work with the trace of the composition of these linear transformations based on the adjoint action of the two elements, just the product of the two matrices. Okay, so what we'll do is we'll use this theorem here. So we want to show that kappa is non-degenerate, and we'll do that by supposing that it is degenerate and showing that, well, in fact, whatever element showed the degeneracy has to be the 0 element. So in other words, we're going to do this. So let's suppose we've got an x inside of SLNC such that kappa of xy is equal to 0 for all y in SLNC. Okay, nice. So in particular, kappa of x and then a basis element of SLNC is equal to 0. But there are two flavors of basis elements. There's one that looks like this. So I'll call this EKL, where k is not equal to L. So this is a matrix where the KL entry is equal to 1 and all of the other entries are non-zero, or are equal to 0, I should say. And I'm saying that k is not equal to L here because otherwise you would be on the diagonal and the trace would be non-zero. Okay, so that's one type of basis element. And then another one goes like this. So, and kappa of x EKK minus ELL is equal to 0. So that's another brand of basis element, is this difference of two matrices that have a 1 in one spot on the diagonal and a -1 in another spot on the diagonal. And here, k is also not equal to L. Okay, good. And so next up, what we'll do is we'll write x in the following form. So this is going to be the sum over all I and j of aij, eij, where eij is this matrix where 1 is in the ij component, and then aij is just a number. And of course, we've got this trace rule here that a11 plus a22, so on and so forth, is equal to 0, given the fact that we are inside of SLNC. Okay, and now let's do the calculation. So we know that 0 is the same thing as kappa applied to x and EKL, like we had up here. But then this is going to be 2 times n times the trace of x times EKL. But I can write that as the sum as I and j go between 1 and n, and here we have aij, and then eij, ekl, just by the linearity of a matrix product. Okay, so that's looking good at the moment. But now, for these matrices that have a 1 in a single entry and 0 everywhere else, there's a standard rule for multiplication. And let's recall that goes like this. This is delta jk times EIL, where EIL is another one of these matrices, and delta jk is the Kronecker delta symbol. So in other words, that's equal to 1 if j is equal to k and 0 otherwise. Okay, so well, what is that going to do? That's going to collapse this sum, which is a double sum, to a single sum and fix j equal to k. So that's going to give us 2 times n, and then we're going to have the trace, and then the sum as I goes from 1 to n of aik, because again, we're fixing j equal to k. And then we have EIL here, just again by that rule that I have in pink. But now we want to add up all of the diagonal entries here, but observe that there's only one diagonal entry, and that's the entry when I is equal to L. So that means, well, if you sum up one thing, you just get that element. So this is going to be 2n and then ALK. Okay, nice. So now looking at this extreme left and right hand side of the equation, we see that pretty clearly we have ALK is equal to 0 for all L not equal to K. So in other words, this matrix right here is a diagonal matrix. So in other words, if we've got this X that makes kappa degenerate, then that X is diagonal. Okay, so now let's move on to looking at this other condition over here. Okay, so this first condition here, which is the condition based off of the basis elements of SLN that have non-diagonal entries, gave us that X had to be a diagonal matrix, which means we can write it as a sum of these diagonal matrices with a single 1 and the rest 0. But then let's recall that since X is itself inside of SLN, we know its trace is 0. In other words, if we sum up all of the diagonal entries, we get 0. Okay, so now let's use this second condition here. So let's see, we'll have 0 is equal to kappa of X and then EKK minus ELL. Okay, so now putting this all together, that's going to be 2n times the trace of, so now we're going to have the sum as I goes from 1 to n of AII, EII, EKK, and then minus this sum as I goes from 1 to n of AII, and then EII, ELL. Again, just kind of pushing everything together. But now we'll use this same product that we did before for the rules for multiplying these basis matrices, if you will. And what this is going to end up giving us is 2n times, well, let's see what it'll be. So this is going to be AKK minus ALL. So let's see, that's going to be true for all k not equal to L. So let's maybe move that over here. So we also have A11 minus A22 is equal to 0. A11 minus A33 is equal to 0. A11 minus A44 is equal to 0. All the way up to A11 minus ANN is equal to 0. Oh, but observe that that means that A22 is the same thing as A11, A33 is the same thing as A11, and so on and so forth. In other words, we have AII is equal to A11, meaning if we plug all of that up here, we'll see that adding all these together tells us that n times a11 is equal to 0, meaning that a11 is equal to 0. And that collapses all of these to be equal to 0. So in other words, aii is equal to 0 for all I. But that means all of the entries of x are equal to 0, the diagonal and the non-diagonal entries. That means that x is equal to 0. But that's exactly what we needed for this killing form to be non-degenerate. But again, by our theorem from last time, that means that SLN is semi-simple. Okay, so now that we've worked this out computationally, let's start looking at the types of things that we need to look at to classify these semi-simple Lie algebras more abstractly. Okay, so now let's keep going. So let's suppose H is an abelian subalgebra of L with only semi-simple elements. Recall that an element is said to be semi-simple if its adjoint action is diagonalizable. Then next up, let's recall the definition of a weight. So alpha is in H star, then we can define this L alpha to be the set of all x in L, where bracket of H with x is alpha applied to H times x for all H in H. Recall that H star is the set of all maps from H to the complex numbers. That makes this alpha H a number. That makes this x a simultaneous eigenvector for every element of H. Well, for add H with H in H. And the eigenvalue depends on, well, it's going to depend on this element over here from H star. Now, technically, alpha is called a weight if and only if this L alpha is non-trivial. Okay, so let's also recall that, or let's also note that we could define this thing L0 to be everything that commutes with the elements from H. So obviously that's going to include H, but it could also include some other stuff as well. Next up, let's define this capital Phi to be, well, they're going to be all of the non-zero weights. So in other words, we've got alpha in H star, where alpha is non-zero and L alpha is also non-zero. Then, well, we can decompose L as L0 plus the direct sum over all of these L alphas. And this all follows from stuff that we did previously. Okay, so now let's look at a couple of examples. Let's start with a very simple example of L equals SL2. So if we're looking for an abelian subalgebra, then, well, that subalgebra is simply going to be H equals this CH. In other words, the one-dimensional vector space spanned by H, where H is this diagonal matrix with 1 and -1 on the diagonal. Then, well, let's recall that E, or H bracketed with E, is equal to 2E, where E is, of course, equal to this matrix right here, 0, 1, 0, 0. And then, of course, we'll also define this F as 0, 0, 1, 0. And then we have H bracketed with F as -2F. So that provides a little bit of motivation. So perhaps now we'll define this element H, or alpha in H star, defined by alpha evaluated at H equals 2. Okay, but then, well, let's notice that we have E is in fact an element of L alpha here. I think that's pretty clear just based off of this, because we have H bracketed with E is equal to alpha of H times E. It's 2E. And then furthermore, we have F is an element of L minus alpha. And that's because we have H with F is equal to minus alpha H with F. Okay, so now putting this all together, we have the following decomposition. So SL2C is decomposed as L minus alpha, direct sum with H, direct sum with L alpha. So we've got the negative part, the diagonal part, H, and then the positive part, if you will. Okay, Good. Now let's look at a SL3 example before we move on to a general result or two. Okay, so now we're gonna look at this SL3 example. So I'm gonna use slightly different notation here. I'll use this fancy G and that fancy H instead of L and H. This is just some other kind of standard notation so that you're familiar with it. So let's let H be the span of H1 and H2, where H1 is this diagonal matrix with a 1 and a -1 and a 0, and H2 the diagonal matrix with 0, 1, and -1. Furthermore, we'll take E1, E2, and E3 and F1, F2, and F3 to be defined as follows. E1 has a 1 in this entry in the first row, second column. E2 in the second row, third column, and E3 in the first row, third column. And then F1, 2, and 3 are simply the transposes of E1, 2, and 3. Then next up, let's define some elements of H star. We'll call them epsilon I. And what epsilon I does is it takes an element from H and it extracts, well, whichever entry the I corresponds to, where we think about these diagonal entries as A1, A2, and A3. And then, well, we've got this chart over here of what epsilon I does to Hj, if you will, where those are the basis elements for our Cartan subalgebra, is what we'll end up calling it eventually. Okay, so now let's do some example calculations. So let's take H1 with E1 and observe that if we do that, we're gonna get 2 times E1. And then if we do, let's see, H1 with, or sorry, maybe H2 with E1, what will we get? Well, we're gonna in fact get minus E1. And I'll let you do that calculation. It's pretty straightforward. But now, well, what we would like to do is hope that E1 is inside of, well, one of these like G alphas or L alphas, depending on what notation you're using. And perhaps we could build those from these epsilons. And we have to be able to build those by these epsilons just based on the epsilons are essentially a basis for the H star. Okay, and this is how it works. So notice that 2 is the same thing as 1 minus -1, but that's going to be epsilon 1 minus epsilon 2 evaluated at H1 times E1. So epsilon 1 H1 is 1. Epsilon 2 H1 is -1. You subtract those, you get 2. And then, well, this is going to be the same thing. It's going to be epsilon 1 minus epsilon 2 evaluated at H2 times E1. That's because epsilon 1 of H2 is 0 and epsilon 2 of H2 is 1. So you get a -1 there. Okay. And then maybe if you introduced a little bit of notation, and here I'm going to use like some standard notation. If you set alpha 1 equal to epsilon 1 minus epsilon 2, then what we would have here is E1 is inside of G alpha 1. And then, well, while we're at it, I'd like to notice that there are some other kind of standard names for this vector E1, or this matrix E1, if you will. Some other names would be like this. E1 is sometimes written as E alpha 1, and it's also sometimes written as X alpha 1. So again, that's just so that we're familiar with some different notations. Okay, so, and then, you know, very similarly, we could do a calculation and we end up with the following. And I'll let you do this, but you get F1 is inside of G minus alpha 1. Okay, good. Now let's do another round of calculation. And well, let's observe that if we were to do H1 with E2, what we would get is, well, that's going to be minus E2. And if we were to do H2 with E2, we're going to get 2E2. That's just, you know, straightforward bracket calculations. And then, well, doing the same thing we kind of did up here, this is in fact epsilon 2 minus epsilon 3 evaluated at H1 times E2. And this is in fact epsilon 2 minus epsilon 3 evaluated at H2 2 times E2. Again, we can see that from the chart over there. And then, well, we could do the same kind of thing that we did over here. We could set alpha 2 equal to epsilon 2 minus epsilon 3. And what we would have here is E2 is inside of G alpha 2. And then very, very similarly, F2 is inside of G minus alpha 2. And then, well, while we're at it, let's recall some of the other notation here. Some of the other notation would be something like this. So E2 is sometimes written as E alpha 2, which is X alpha 2. And then while we're at it, F2 is sometimes written as F alpha 2 or X minus alpha 2. That's another way of writing those vectors. And then, well, just to finish all of this off, we've got one last thing, and that's the following. And I'll just write this all at once. If you take H bracketed with E3, what you'll get is epsilon 1 minus epsilon 3 evaluated at H, E3, which motivates the following. We could set alpha, you might say alpha 3 equal to this, but observe that this epsilon 1 minus epsilon 3 is in fact the sum of alpha 1 and alpha 2. So what we have here is E3 is inside of G alpha 1 plus alpha 2. And similarly, F3 is inside of G minus alpha 1 minus alpha 2. And that provides, well, motivation for kind of the other notation, like we saw with these other vectors, as E3 is often written as E alpha 1 plus alpha 2 or X alpha 1 plus alpha 2. And then F3 is often written as F alpha 1 plus alpha 2 or X minus alpha 1 minus alpha 2. Okay, so we've got this example with SL3. Now what I'd like to do is do some maybe more general results. So now for our first of kind of general results towards kind of our main goal. So let's suppose that alpha and beta are inside of H star. Then we have the following three results. So the bracket of L alpha with L beta is contained in L alpha plus beta. That means if we've got an element from this first one and an element from the second one, then when you bracket them, you get an element from this third one. So let's maybe go ahead and prove that first. So let's suppose that X is in L alpha, Y is inside of L beta, and then we're going to need an H inside of H, just based off of how all of this works. And now let's take the bracket of H with the bracket of X, Y. Maybe before we do that, let's go over here and just quickly recall what it means for X to be an L alpha, Y to be an L beta. So this means the bracket of H with X is equal to alpha H times X. And then the bracket of H with Y is equal to beta H times Y. Again, that's by this definition right here. Okay, so now what we'll do is pull this into two pieces using the Jacobi identity. So that's going to give us the following. We're going to have the bracket of H with X and then Y, and then plus the bracket of X with the bracket of HY. Okay, so I think that's looking pretty good. But now, well, what is this object? So this is alpha HX. And then this object right here is beta HY by that brown box. But then recall that we have bilinearity here, meaning that we can factor out the alpha H and factor out the beta H. And then furthermore, then we'll just be left with the bracket of X with Y. And so after all is said and done, this is going to give us alpha plus beta applied to H times the bracket of X with Y, meaning that the bracket of X with Y is in fact inside of L alpha plus beta as needed. Okay, so that's this green dot done. Now let's move on to the magenta dot. So what's that saying? Well, that's saying that, well, if you apply kappa to something from L alpha and something from L beta, you get 0, as long as alpha plus beta is non-zero. Okay, so let's see. We're gonna start by using this. So alpha plus beta is non-zero. That means it's not the 0 map, but that means it takes on a non-zero value somewhere. Recall that it acts on elements from H. So in other words, there exists an H inside of H such that alpha plus beta applied to H is not equal to 0. Okay, good. Then also, while we're at it, let's take an X inside of L alpha and a Y inside of L beta. Now let's look at kappa evaluated at X, Y. We want this to be 0. That would prove this magenta dot result. Okay, so what I'm going to do is multiply by 1. And I'm going to multiply by 1 in the following form. It's going to be alpha plus beta evaluated at H over alpha plus beta evaluated at H. And then, well, of course, we still have this kappa of X, Y. So now let's write this as 1 over our alpha plus beta applied to H, and then distribute the rest of this stuff out. So we're going to have alpha applied to H, kappa of X, Y. But by linearity, I can bring that alpha applied to H inside. So I've got kappa of alpha applied to H, X, Y. And then similarly, I have kappa of X, and then beta applied to H. Okay, great. But now what I'll do is, well, I've got to bring some stuff down first. So alpha plus beta applied to H. And then here, this is going to be my kappa of HX with Y. And then kappa of, let's see, X with Y. Let's see, I left a Y out here. Good. So I think that's looking pretty good. And then I'm summing these. Okay, great. Now, by a property that we proved about the killing form, an object like this, or this, sums to 0. And maybe you could very, very easily see that as follows. So we could take this kappa of X and then bracket HY, and you could bring a minus sign out here, and then switch this to YH. Okay, good. And then after doing that, these two are equal directly from the earlier result that we proved. But now we're taking the difference of two things that are equal, meaning we get 0. But look, starting here and ending down there is exactly what we need for this thing to be, or to prove this magenta dot. Okay, so now let's move on to the last thing, the blue dot, which says that kappa restricted to L naught is non-degenerate. Okay, so how can we do that? So it's going to go like this. So let's take an X inside of L0, and then since kappa itself is non-degenerate, what that tells us is there exists a Y inside of L such that kappa of X with Y is non-zero. Okay, good. And so, well, why is that? Well, if that did not hold, then kappa would be degenerate on the whole Lie algebra. But it can't be degenerate on the whole Lie algebra because we're assuming that L is semi-simple by our previous result. Okay, so now next up, let's do the following. Let's write Y as Y naught plus the sum over all alpha in this phi of Y sub alpha, where we're using this result down here. So in other words, we have Y naught in L naught, and then we have Y alpha inside of L alpha. Okay, good. And then next up, what I'd like to note is by the magenta dot, what do we know? Well, we know that kappa of X with y alpha is equal to 0. So again, that's by this magenta dot, because alpha is non-zero. And then, well, you could just say that beta is 0. So like alpha plus 0 is non-zero. I think that's pretty straightforward. Okay, and then we can finish it off kind of. Let's observe that that's going to be equal to kappa of x with y minus the sum over all alpha of kappa of x with y alpha, just by inverting this equation. But this part is all 0, this sum over all of the alpha. All of those terms are 0. But this one is non-zero. So we've got something non-zero minus a bunch of zeros, so we have something non-zero. But let's look at what we've done here. We took an arbitrary x in L naught, and then we found an element y naught from L naught, where when we did kappa of x with y naught, we got something that's non-zero. But that's exactly what we need for this proof of non-degeneracy. Okay, so now I'm going to leave you with some homework exercises. So here are two nice exercises based on what we saw today. So let's suppose we've got a non-zero element of H star, and then we have X inside of L alpha. Then we want to show that add X, that adjoint action, is nilpotent. Next up, let's fix L to be SL4C. So those are 4x4 matrices with trace 0. So the standard thing to do would be to decompose L with respect to H, which is the subalgebra of all diagonal matrices. But let's do something a little bit different. Let's decompose it with respect to some smaller subalgebras. The first being H1, which, well, those are going to be diagonal where the last two entries are 0. Recall that the trace still has to be 0. And then let's do it again for H2. And so those are again going to be diagonal, but now the last entry is equal to 0. Okay, that's a good place to stop.